There is a wall standing between you and the end of everything downstream. You cannot see it from your house. You probably don't think about it. But somewhere above the cities, above the valleys, above the farmland and the roads, and the quiet, sleeping towns, there is a dam. And behind that dam is a force that most people will never truly understand. Water does not compress. It does not yield. It does not wait. Every second of every day, it pushes against the concrete, against the rock, against the foundation beneath. And when engineers get it right, nothing happens. The wall holds. Life continues. But engineering history is not a story of things that held. It is a story of the moments when the math was wrong, when the warning signs were ignored, when the ambition of the project outgrew the caution of the people building it, and when the water finally found its way through. These are the stories of the deadliest dam failures in human history, and they are not stories about incompetence. They are stories about what happens when human beings build things at the edge of what is physically possible, and then push just a little further. To understand what makes a dam fail, you first have to understand what a dam actually does. A dam is not simply a wall. It is a structure designed to hold back a reservoir of water that is constantly, relentlessly trying to move downhill. The force pushing against the dam is called hydrostatic pressure, and it is not uniform. Near the surface of the reservoir, the pressure is relatively low. But as depth increases, pressure builds. At the base of a large dam, the water pressing against the foundation can reach pressures measured in the hundreds of tons per square meter. The dam resists this through its own mass, its shape, and the strength of the rock or earth it sits on. And that last part, the foundation, is where history has been the most unforgiving. We begin in California, 1928. The St. Francis Dam sits 65 kilometers north of Los Angeles in the San Francisco Canyon. It is a curved concrete gravity dam, 212 feet tall. It was designed and built by William Mulholland, one of the most celebrated engineers in American history, the man who brought water to Los Angeles, a man whose reputation was considered beyond question. But reputation does not hold back water. On the night of March 12, 1928, just hours after Mulholland himself inspected the dam and declared it safe, the St. Francis Dam collapsed. The failure happened almost instantaneously. 12 billion gallons of water were released into the canyon below in a matter of minutes. The flood wave traveled 54 miles to the Pacific Ocean. It killed an estimated 430 people, and it destroyed nearly everything in its path. So what happened? The dam's foundation had been built on two different rock types on either side of the canyon. On one side, an ancient landslide zone. On the other, a type of sedimentary rock that absorbs water and expands. When the reservoir filled, that rock began to soften. The foundation literally lost its grip. Water began seeping beneath the dam. Uplift pressure, water forcing its way under the base of the structure, began to reduce the effective weight holding the dam in place. And then the dam simply slid. The St. Francis disaster ended William Mulholland's career. He accepted full responsibility, and the failure gave American engineering one of its most important lessons. The strength of a dam is only as good as the ground beneath it. If you're finding this kind of engineering history fascinating, the intersection of physics, ambition, and consequence, consider subscribing to Next Build. We break down the mega projects, infrastructure systems, and engineering disasters that have shaped the modern world. There's a lot more in this video, and a lot more on this channel. Now we travel to northern Italy. 1963. The Vajont Dam sits in the Piave River Valley in the Dolomite Mountains. At the time of its completion, it is one of the tallest arch dams in the world, 261 meters high, a marvel of thin-shell concrete engineering. An arch dam works differently from a gravity dam. Instead of relying purely on mass to resist pressure, the arch shape redirects the force of the water outward into the walls of the canyon on either side. Less material, greater height, elegant physics. But the Vajont Dam did not fail because of the dam itself. It failed because of what was above it. The reservoir sat in a valley surrounded by unstable mountain slopes. Geologists had flagged concerns about the stability of Monte Toc, the mountain directly above the reservoir, during the planning stages. Their warnings were noted and then set aside because the dam was already under construction, because the project was already funded, because stopping would have been expensive and embarrassing. So the dam was filled, and as the water level rose, it saturated the base of the mountain. The rock absorbed the water. The ancient clay layers beneath the slope softened. And on the night of October 9th, 1963, 260 million cubic meters of rock and debris separated from Monte Toc and fell into the reservoir. Not slowly, in approximately 45 seconds. The displacement wave that followed did not go over the dam in the way you might imagine a flood goes over a wall. It surged over the top with a force so concentrated that it launched water nearly 250 meters into the air on the downstream side. The wave reached the town of Longarone in a matter of minutes. 1,910 people died. The dam itself survived. The concrete arch held. But survival meant nothing. What engineers learned from Vajont was something that still shapes project planning today. A dam does not exist in isolation. The entire geological system around it, the slopes, the rock formations, the ancient landslide zones that may have been stable for 10,000 years, all of it becomes part of the engineering problem the moment you fill a reservoir. 3 years after Vajont, on the other side of the world, another dam was failing, not from a landslide, but from something far more common and far more insidious: rain. The Banqiao Dam in Henan Province, China, was built in 1952 on the Ru River. It was an earthen dam, a compacted embankment of soil and clay rather than concrete. Earthen dams are one of the oldest forms of water infrastructure in human history. They rely on the density of their construction and the integrity of their core to prevent water from seeping through. Banqiao was considered one of China's most important flood control projects. Soviet engineers helped design it. It was built during a period of enormous national ambition. And when local engineers expressed concerns about its spillway capacity, its ability to discharge water fast enough during extreme floods, those concerns were dismissed. One engineer, Chen Xing, specifically warned that the number of spillways was insufficient. He was removed from the project. In August of 1975, Typhoon Nina made landfall over China. What followed was a meteorological event of almost unimaginable scale. In 24 hours, 1,000 millimeters of rain fell in parts of Henan Province. To put that in context, that is roughly the entire annual rainfall for those regions, falling in a single day. The Banqiao Reservoir filled faster than its spillways could discharge. At the same time, downstream dams were sending urgent signals that they were also filling beyond capacity. A cascading failure began, dam after dam overtopped. The wave reached Banqiao at 1 in the morning on August 8th. The dam overtopped and failed. The flood wall of water that was released was approximately 10 kilometers wide and 3 to 7 meters high. It traveled across the Huai River Basin at extraordinary speed. The official death toll was later revised to approximately 170,000 people. Some estimates suggest the number was higher. It remains to this day the deadliest dam failure in recorded human history. And it was caused not by a geological anomaly, not by a once-in-a-millennium earthquake. It was caused by a spillway that was too small, by a warning that was ignored, by a system that could not discharge water as fast as nature could deliver it. 1 year after Banqiao, in the American state of Idaho, a different kind of earthen dam was failing in almost the same way. The Teton Dam sat on the Teton River. It had been constructed by the United States Bureau of Reclamation, one of the most experienced dam-building agencies on Earth, and it was failing before it had ever held water for a full season. The dam was built in a canyon of highly porous volcanic rock. As the reservoir filled for the first time in the spring of 1976, water began seeping through the rock at the dam's abutments, the points where the dam connected with the canyon walls. On June 5th, workers noticed a wet spot on the downstream face of the dam, then a small boil of muddy water, then a larger seep, then a hole. The process they were watching had a name: piping. Piping is one of the most dangerous failure modes in earthen dam engineering. It begins when water finds a pathway through the interior of a dam or its foundation. As it moves through, it carries fine soil particles with it. The pathway grows larger, more water flows, more material is removed. The process accelerates. By the time a piping failure becomes visible on the downstream face, it is almost always too late. On June 5th, 1976, the Teton Dam collapsed. 2,000 people lost their homes. 11 people died. The dam had never fully operated. It failed on first fill. The subsequent investigation found that the Bureau of Reclamation had underestimated the permeability of the volcanic rock beneath the abutments. The geological data was available. The risk had simply not been weighted correctly. Not all dam disasters result from catastrophic collapse. Some unfold slowly, over hours, over days, in ways that are almost worse, because they give you just enough time to watch what is coming. In February of 2017, the Oroville Dam in Northern California, the tallest dam in the United States, began experiencing a crisis with its primary spillway. A section of the concrete surface had eroded away, leaving a massive crater in the spillway floor. Engineers attempted to continue releasing water through the damaged section while reducing inflow from the reservoir. But the erosion continued. The damaged spillway was eating itself. As reservoir levels climbed, operators were forced to activate the emergency spillway, an unlined hillside that had never been used in the dam's nearly 50-year operating history. Within hours, the emergency spillway began to erode too. The hillside itself was being carved away by the water flowing over it. If the erosion continued, the emergency spillway headwall, the concrete wall at the top of the hillside, could fail. And if that structure failed, it would send an uncontrolled wall of water toward the communities below. Nearly 188,000 people were ordered to evacuate. The emergency ended when rainfall temporarily reduced inflow and operators were able to lower the reservoir. No one died. But the Oroville crisis revealed something critical about dam safety in the modern era. Many of the largest dams in the United States were built in the 1950s, 60s, and 70s. Their infrastructure is aging. Their inspection records are incomplete. Their emergency spillways, in many cases, had never been designed to handle the kind of rainfall events that climate patterns are now delivering. Oroville was not a failure of engineering theory. It was a failure of maintenance, a failure of funding, a failure to take seriously the slow decay of something enormous. We return to Europe, France, 1959. The Malpasset Dam sits on the Rewrote River in the south of France, near the city of Fréjus. It is a double curvature arch dam, thin, elegant, a product of the most advanced concrete shell engineering of its time. On December 2nd, 1959, after a period of heavy rain, the Malpasset Dam failed completely. It did not leak. It did not overtop. It shattered. The entire left abutment of the dam moved. The rock formation it had been anchored into, which had appeared solid and reliable during construction, contained a thin, hidden fault line running at an angle beneath the foundation. As the reservoir filled and hydrostatic pressure increased, water worked its way into that fault. The pressure built, the rock shifted, and when the abutment lost its connection to solid ground, the arch had nothing to push against. The dam collapsed in seconds. A wall of water 40 meters high swept downstream. 423 people died. The Malpasset disaster fundamentally changed how geotechnical surveys were conducted before dam construction. Before Malpasset, visual inspection and surface sampling were considered adequate. After Malpasset, deep core drilling, fault mapping, and pressurized water testing became standard requirements for any arch dam foundation site. That protocol exists today because of the 423 people who died on the Rewrote River in 1959. There is a pattern running through every one of these stories. It is not incompetence. It is not malice. It is something more human than either of those things. It is the tendency to believe that what has not yet failed will not fail. Mulholland inspected his dam the morning before it collapsed and said it was safe. The geologists who raised concerns about Montauk were overruled by a project already in motion. Chen Xing was removed from Banqiao because his warnings were inconvenient. The Bureau of Reclamation built Teton on volcanic rock it had not fully characterized, and Oroville's emergency spillway spent 5 decades as an untested assumption. In each case, there was data. There were warning signs. There were engineers who understood the risk. But the momentum of large infrastructure projects, the politics, the funding, the national pride, the sunk costs, creates a gravity of its own, and that gravity pulls toward completion, toward reassurance, away from caution. Modern dam engineering codes are not abstract documents. They are written in the language of specific disasters. Foundation investigation protocols, Malpasset. Spillway capacity requirements, Banqiao. Piping failure detection systems, Teton. Geological survey requirements for reservoir slopes, Vajont. Abutment testing standards, St. Francis. Every clause in those codes represents a moment when the physics won, when the warning was too late, when a valley downstream lost everything, and the engineers who survived those events sat down and tried to write rules that would prevent the next one. Today, there are approximately 50,000 large dams operating around the world. Many of them are aging. Many of them are in regions experiencing rainfall patterns that are shifting beyond the historical data used to design them. Many of them have emergency spillways that have never been tested, and many of them sit above communities whose residents have never been told about the infrastructure failure scenarios documented in the dam's own safety files. This is not cause for panic. Dams are engineered systems. They are monitored. They are inspected. Modern sensor networks can detect seepage changes measured in fractions of a millimeter, but monitoring is only as good as the funding behind it, and deferred maintenance is a risk that does not appear on the surface. It appears one morning as a wet spot on the downstream face of something enormous. The dams in these stories were not built by careless people. They were built by engineers who believed in what they were doing, who worked at the edge of what was understood, who were operating in eras before computational modeling, before satellite imaging, before the failure data sets that now inform every major design decision. They were doing what engineers have always done, pushing forward, building things the world had never built before. And sometimes the world pushed back. The lesson of dam engineering history is not that we should build less. It is that we should listen more carefully to the data, to the geologists, to the engineers who raise concerns at inconvenient moments, and to the slow, quiet signals that something enormous is no longer entirely in our control. Every bridge you drive across, every tunnel you pass through, every dam that holds water, above a valley where people are sleeping tonight. These are not permanent things. They are temporary agreements between human engineering and natural force, maintained by funding, sustained by inspection, dependent on the willingness to hear difficult truths before the moment when only the water speaks. If this kind of engineering history stays with you, if you find yourself thinking differently about the infrastructure around you, subscribe to Next Build. We explore the mega projects, engineering disasters, and infrastructure systems that shape the world most people never think to question. Leave a comment below with the dam failure that affected you most in this video. And if you want to keep going, there is another documentary waiting for you right now. The infrastructure around you is more fragile than it looks. And understanding it, really understanding it, is the first step toward demanding something better.